Welcome again to the course on audio signal processing for music applications. This week we're talking about applications. We're talking about how to use the models we have been studying throughout the course for the application of sound transformation. So we aim at manipulating sounds and changing different aspects of it. In the first demonstration class, we exemplified the idea of morphing using the short time Fourier transform. In the last class, we talked about time scaling, how to change the duration of the sound using the sinusoidal model. And in this class, I want to talk about pitch changes, how to change the frequencies of a sound, and we will use the harmonic plus stochastic model. So we'll be basically changing pitch-related information of harmonic sounds. In order to use the harmonic model, we need to understand a little bit the sound. So for example, if we start with this saxophone sound, let's listen to this. Okay, in order to define especially the window size, we need to know the ranges of fundamental frequencies that are present here. So a good way to do that is to look at the spectrogram of the sound and basically zoom in to the first harmonic so that we see basically the fundamental frequency, which is the first line of this harmonic series, and kind of see which is the lowest and highest values in here. So it's better to use a bigger window size so we see a more refined line, and with this, okay, we have a pretty good view of this line. And clearly the lowest sound would be this note here, more or less. So that's around, if we see, let's say around 450 hertz, and then the highest is this note here, which is around 600 and something hertz. Okay, so this is good information for now defining the parameters of the harmonic plus stochastic model. So let's go to the SMS Tools Models GUI, and let's go directly to the harmonic plus stochastic model, and we will open this same file, which is this sax phrase, the short version of it. Okay, now we have to choose the parameters. The window Blackman is a good choice because it has a good low-level side lobes. Now, in order to decide the window size, well, it's good to basically go to a terminal, and from IPython we can just quickly do calculations. So for example, we can just say, okay, the Blackman window has 6 beams in the main lobe. We multiply by 44,100, and we said that the lowest frequency was around 400 and something hertz. So let's, in order to be safe, let's say, okay, 400 hertz. So 400, and this is a window size that is appropriate for a frequency of 400, the lowest, which is the meaningful one because it's the longest window that we will need. Okay, so we will put as window size, let's say 661, an odd size. FFT size, well, let's make a big one, so we have 0 padding, let's 2048. The threshold, it really doesn't need to be that low, but let's leave it, so we have a lot of harmonics there. The minimum duration of sinusoidal tracks, 0.1, that's fine. Maximum number of harmonic. The maximum number of harmonics that there will be 44,100 divided by 400. Okay, that would be if it had all the harmonics, so it's 110, but of course this is the lowest frequency, and this is really if we would have harmonics all the way through. So 100 would be fine. Then we need to define the range of the fundamental frequency, so we can put the one we said, it was around 400, and the other was around 600 and something, so to be safe, let's say 650. Okay, this is an error threshold to identify the fundamental frequency. Maybe let's be a little more flexible, let's put 7, and this deviation That's fine like this. And the stochastic approximation for the residual, we don't need to be too smooth. We don't need to do data compression. So if, let's say, if we have 0.4, that should be okay. Okay, let's compute it now. Okay, so this is the result. We have the original signal, the analyze, the harmonics plus the stochastic, and the synthesize. Let's listen to the different components of it. The sinusoidal component. It clearly captures most of the sound. Then let's listen to the stochastic. Well, it's very soft, but it's there, so it's a relevant component, and of course the sum of the two. Okay, so this is a good starting point to now run the transformation. So let's go to, let's quit this. Let's try to remember these parameters. And now we will go to the other directory where we have the transformations interface. And let's type Python and the transformation GUI. Okay, so this is the GUI for the transformations, and let's go directly to the HPS model with the transformations. And well, it's already by default the sax phrase is here. So let's use the parameters that we use. If I remember, was 661. We did FFT of 2048. The threshold was minus 100. Minimum sign duration was that. A number of harmonics 100. This minimum was frequency, we said 400, and maximum was 650. F0 detection, the F0 error threshold was 7, and the stochastic factor we put 0.4. Okay, now we can analyze, and this would definitely do the same thing that we did before, so we can check that the analysis is correct. Okay, that's exactly the same sound that we heard before. So now we can start playing around with the transformations, and we have two possibilities for changing the frequencies and one for changing the time. So for the time, we're not interested in changing the time, so let's say the time as 0, 0, 1, 1. So that means that it's not changing anything. Okay, now in frequency scaling, we have two frequency transformations. Given that we are in a harmonic sound, we know where the harmonics are, and that's a great advantage compared with the sinusoidal model. So in fact, these type of changes could be done with the sinusoidal model, but of course then we are restricted to some transformations. And for example, the frequency stretching is not possible with the sinusoidal model because we don't know which sinusoid corresponds to which harmonic. Okay, let's just first let's just use the scaling first. So let's have here again without any transformation. So if we put 0, 1, 1, 1, that means that there is a frequency stretching of 1, so it means no stretching at the beginning and at the end. And then, okay, in the frequency scaling, well, let's start with by downloading or sort of decreasing the pitch of this sound, for example, 0.8. And so it's at time 0, we will have 0.8, and at time 1, we'll have also 0.8. Okay. And a very important parameter is this timbre preservation. This timbre preservation, what it does, it tries to preserve the shape of the spectrum of the harmonics. If we put 1, it preserves the harmonic shape, so it should sound more natural than if we put 0, in which 0 we just transpose everything, and so the magnitudes will be affected. So let's apply it like this. Okay, so we have clearly transposed the harmonics down, so now they are closer together. So let's listen to the result. So it sounds quite natural, even though we have transposed. Mainly because of this timbre preservation, we have maintained quite a bit this quality of the saxophone. And then just to finish, let's make some frequency stretching. So frequency stretching is a kind of to convert the sound into an inharmonic type of spectrum in which we are adding an exponential factor to the harmonic value, let's say. So if we have at time 0, 1, let's say, let's start with 1, and then at the end, let's stretch everything to, let's say, 1 point, let's say 1. Okay, so we will have a stretching factor at the end and not at the beginning. So progressively, the stretching will increase. Let's see what that does. Okay, so we see clearly here that the fundamental has remained the same, and the harmonics, well, we still have maintained the scaling factor, so we are scaling everything down to 0.8, but the harmonics keep getting apart from each other more and more as the time goes on. And clearly at the end, they are not equally spaced, so that's an inharmonic spectrum. Let's listen to that. Okay, so clearly the low frequency is the same, but as time progresses, the sound sounds more inharmonic, kind of more metallic, because the harmonics have been stretched. Of course, we can do a lot of things, so feel free to play around with these parameters, and of course with time scaling. Time scaling is also very powerful once we have been able to analyze the sound with the harmonic plus stochastic model. That's all I wanted to say. So basically, we have talked about the idea of changing the pitch or the frequencies of a sound. First, we use Sonic Visualizer to understand the sound, and then we use the SMS Tools GUI with the harmonic plus stochastic model to change the pitch or the frequencies of a sound. So we have been talking about pitch change. Of course, pitch change can be done with the sinusoidal model, can be done with the harmonic plus stochastic, or the sinusoidal plus stochastic, or with quite a few of the models we have been talking about. And in Audacity also there is some implementations for that. So anyway, so we just presented a little bit of that, an example using the harmonic plus stochastic and the potential for this type of transformations. So I hope you got an idea of that. And now we'll have still another demonstration class in we'll be talking about the harmonic plus stochastic model, but in another type of possibility of transforming sounds, which will be of morphing two sounds, interpolating the two representations of two sounds. So I hope to see you all next class. Bye-bye.